Welcome to Laboratory's e-learning portal. We are going to learn about measurement uncertainty. References: Eurochem, CITAC Guide, CG4, Qualifying Uncertainty in Analytical Measurement. ISO Guide 98, Guide to Expression of Uncertainty in Measurement. NABL 141, Guidelines for Estimation and Expression of Uncertainty in Measurement. ISO, IEC 17025, 2017. It is the requirement as per the standard, ISO 17025, 2017, Clause 7.6 Evaluation of Measurement Uncertainty, which details about identifying the contributions to measurement uncertainty at Clause 7.6.1. Evaluation of measurement uncertainty for all calibrations at Clause 7.6.2. Evaluation of measurement uncertainty at Clause 7.6.3. As per the Clause 7.8.3, Specific Requirements for Test Reports, it is required to report the measurement uncertainty in the same unit of results. This measurement uncertainty plays an important role in the statement of conformity and in decision rules. What is measurement uncertainty? A parameter associated with the result of a measurement or test that characterizes the dispersion of the values that could reasonably be attributed to the measurand. Measurement uncertainty is the expression of the statistical dispersion of the values attributed to a measured quantity. Importance of measurement uncertainty. Why measurement uncertainty is required. It helps in reliability of test results. Increase the trust in the results. It helps in comparison of results generated for same products in different locations or different conditions. It helps in increase the confidence in comparison of results. It indicates the competency of laboratory. What is expanded uncertainty? Product of a combined standard measurement uncertainty and a factor larger than the number 1. The expanded uncertainty provides an interval within which the value of the measurand is believed to lie with a higher level of confidence. What is standard uncertainty? It is the measurement uncertainty expressed as a standard deviation. What is relative standard uncertainty? Relative standard uncertainty is the standard uncertainty divided by the value. It is UX divided by X. What is combined uncertainty? It is square root of sum of square of relative standard uncertainties. What is expanded uncertainty? It is combined uncertainty multiplied by coverage factor K. The uncertainty of measurement is a quantitative indication of the analytical variability of a result. It demonstrates how well the result represents the value of the quantity being measured in the test portion. The uncertainty may to be taken into account when interpreting data. For example, observed differences in results may be accounted for the uncertainty associated with the results rather than real differences in properties or performance. Thus, if two competent laboratories examine different subsamples from the same sample source by the same method and obtain numerically different results, these results may not be different when uncertainty measurement is taken into account. Identification of sources of measurement uncertainty. When calculating the measurement uncertainty, it is important to identify the sources from where uncertainty can be accounted. Fishbone diagram tool can be utilized to identify the sources. Identification of uncertainty from manpower, such as replicate analysis. Equipment calibrations, methods, environmental conditions, sampling, materials, and consumables such as reference standards, chemicals purity etc. Other factors or sources also should be considered for calculation of measurement uncertainty. Instrument effects. Instrument effects may include, for example, the limits of accuracy on the calibration of an analytical balance. A temperature controller, that may maintain a mean temperature, which differs from its indicated set point. An auto-analyzer, that could be subject to carry-over effects. Reagent purity. The concentration of a volumetric solution will not be known exactly, even if the parent material has been assayed, since some uncertainty related to the assaying procedure remains. Many organic dyestuffs, for instance, are not 100% pure and can contain isomers and inorganic salts. Sample effects. The recovery of an analyte from a complex matrix, or an instrument response, may be affected by the composition of the matrix. Analyte speciation may further compound this effect. The stability of a sample or analyte may change during analysis because of a changing thermal regime or photolytic effect. When a spike is used to estimate recovery, the recovery of the analyte from the sample may differ from the recovery of the spike, introducing an uncertainty, which needs to be evaluated. Computational effects is the selection of the calibration model. Example, using a straight-line calibration on a curved response leads to poorer fit and higher uncertainty. Truncation and round-off can lead to inaccuracies in the final result. Blank correction. There will be an uncertainty on both the value and the appropriateness of the blank correction. This is particularly important in trace analysis. Operator effects. Possibility of reading a meter or scale consistently high or low. Random effects. Random effects contribute to the uncertainty in all determinations. The standard uncertainty of the measurand depends upon the standard uncertainties of the input quantities and also upon their correlation. The uncertainty of measurement associated with the input estimates is evaluated according to Type A and Type B methods of evaluation. This is the flow chart for measurement uncertainty calculation. Step 1. Identify the sources of measurement uncertainty. Step 2. Calculation of Type A measurement uncertainty. Step 3. Preparation of uncertainty budget table and calculation of Type B measurement uncertainty. Step 4. Calculation of combined measurement uncertainty. Step 5. Calculation of expanded measurement uncertainty. Step 6. Expression of measurement uncertainty with test or calibration results. Type A uncertainty shall be taken from repeatability of test results from the selected sample. Type A evaluation of standard uncertainty applies to the situation when several independent observations have been made for any of the input quantities under the same conditions of measurement. If there is sufficient resolution in the measurement process, there will be an observable scatter or spread in the values obtained with a number of statistical independent observations. The estimate of measured value M is X. Calculate the arithmetic mean of the individual observed values. Calculate the standard deviation for the obtained measured values. Further standard uncertainty shall be obtained as follows. Standard uncertainty is equal to standard deviation by square root of number of replicates. Relative standard uncertainty shall be calculated as follows. Relative standard uncertainty is equal to standard uncertainty divided by mean value. Obtained relative standard uncertainty shall be used for calculation of combined uncertainty. Example of Type A uncertainty. Type A uncertainty calculation for oil content in X product. 5 replicate testing results are considered for calculation. Replicate 1, obtained result 43.23. Replicate 2, obtained result 43.33. Replicate 3, obtained result 43.11. Replicate 4, obtained result 43.11. Replicate 5, obtained result 43.71. Obtained mean value 43.36. Standard deviation value 0.2271563. Standard uncertainty is equal to 0.2271563 divided by square root of 5 and obtained standard uncertainty value is 0.10158874. Relative standard uncertainty is equal to standard uncertainty 0.10158874 divide by mean 43.36, obtained value is 0.00234288. Evaluation of Type B standard uncertainty. Preparation of uncertainty budget table is important to calculate this Type B uncertainty. Uncertainty estimation is simple in principle. The following are summarized tasks that need to be performed in order to obtain an estimate of the uncertainty associated with a measurement result. 1. Identify uncertainty sources. 2. Quantify uncertainty components. 3. Calculate combined uncertainty. 4. Calculate expanded uncertainty. For test uncertainty, Type B will be considered from equipment, apparatus, and standard purity like mass of sample, sample preparation, purity of standard, standard preparation etc. For example, balance, volume uncertainties in standard flask used in preparation of standard stock solution, and the pipette volume uncertainties, purities of CRM. Based on the applicability uncertainty will be taken from the calibration certificate and from NIST traceable certificate for reference materials. For calibration uncertainty, the Type B will be considered from reference standards, CRM. The proper use of the available information for a Type B evaluation of standard uncertainty of measurement calls for insight based on experience and general knowledge. Norma distribution division factor is 2, and value is 2. Rectangular distribution division factor is square root of 3, and value is 1.732051. Triangular distribution division factor is square root of 6, and value is 2.4495. When to consider normal distribution. The replicate reading values are more likely to fall near the average value. Where an uncertainty estimate is derived from previous results and data, it may already be expressed as a standard deviation in certificates. However, where a confidence interval is given, with a level of confidence, then divide the value A by the appropriate percentage point of the normal distribution for the level of confidence given to calculate the standard deviation. A specification states that a balance reading is within plus or minus 0.2 mg with 95% confidence. From standard tables of percentage points on the normal distribution, a 95% confidence interval is calculated using a value of 1.96. Using this figure gives a standard uncertainty of 0.1. When to consider rectangular distribution. Rectangular distribution, also called as uniform distribution. If limits of plus or minus a are given without a confidence level, and there is reason to expect that extreme values are likely, it is normally appropriate to assume a rectangular distribution with a standard deviation of a divide by square root of 3. In simple words, where the tolerance limit reported without confidence level is considered as rectangular distribution. Example: 10 ml grade A volumetric flask is certified to within plus or minus 0.2 ml. The standard uncertainty is 0.2 divided by square root of 3 is equal to 0.12 ml. When to consider triangular distribution. If limits of plus or minus a are given without a confidence level, but there is a reason to expect that extreme values are unlikely, it is normally appropriate to assume a triangular distribution with a standard deviation of a divide by square root of 6. Example: 10 milliliters grade A volumetric flask is certified to within plus or minus 0.2 milliliters, but routine in-house checks show that extreme values are rare. The standard uncertainty is 0.2 divided by square root of 6 is equal to 0.08 milliliters. These are the different distribution factors with their log values. Calculation of standard uncertainty. Standard uncertainty is equal to uncertainty or tolerance divided by factor of distribution. Type B uncertainty is equal to square root of ux1 square plus ux2 square plus ux3 square. Combined uncertainty. The type A and type B uncertainty values are individually combined and calculated a combined uncertainty. Wherever the measurements cannot be categorized under generic common measurements, the relative uncertainty is calculated as standard uncertainty divided by the estimated source value. Before combination, all uncertainty contributions must be expressed as standard uncertainties, that is, as standard deviations. Where the uncertainty component was evaluated experimentally, from the dispersion of repeated measurements, it can readily be expressed as a standard deviation. For the contribution to uncertainty in single measurements, the standard uncertainty is simply the observed standard deviation. For results subjected to averaging, the standard deviation of the mean is used. Calculation of combined uncertainty by using standard uncertainty is UC is equal to square root of UA square plus UB square, so on. Calculation of combined uncertainty by using relative standard uncertainty is UC is equal to mean multiplied by square root of UA square plus UB square, so on. In the final step of calculating expanded uncertainty, the combined uncertainty is multiplied by the coverage factor K. The coverage factor will vary, depend upon the confidence level adopted. Coverage factor at 68% confidence level is 1. Coverage factor at 95% confidence level is 2. Coverage factor at 99% confidence level is 3. The numerical factor used as a multiplier of the combined standard uncertainty, in order to obtain an expanded uncertainty. In cases where a normal distribution can be attributed to the measurand, and the standard uncertainty associated with the output estimate has sufficient reliability, the standard coverage factor K is equal to 2 is used. The assigned expanded uncertainty corresponds to a coverage probability of approximately 95%. Degrees of freedom. Degree of freedom is also used to determine the coverage factor from student t-test table. Degrees of freedom are the maximum number of logically independent values, which may vary in a data sample. Degrees of freedom are calculated by subtracting 1 from the number of items within the data sample. Example of calculating measurement uncertainty. It is simple examples, which details about calculation of mean value from the replicate results in the type A uncertainty, calculation of standard deviation from the replicate results, and calculation of standard uncertainty from standard deviation and number of replicates. Calculation of relative standard uncertainty from standard uncertainty and mean of replicate results. Calculation of type B uncertainty. In this first step we need to find of number of components contributing the measurement uncertainty. In this example, balance volumetric flask with the capacity of 25 milliliters and 10 milliliters micropipettes. Take the uncertainty values from respective calibration certificates and calculate the relative standard uncertainty for each component. Further calculation of the combined uncertainty from type A uncertainty and type B uncertainty components. Calculation of expanded uncertainty by multiplying the combined uncertainty with coverage factor K. Generally coverage factors will be used is 2, which is 95% confidence level. This expanded uncertainty is the final uncertainty which will be reported along with the test or calibration results in the same units.